welcome to our video presentation about design of a piping system for cooling process. Our group members are me, Tan Chun Yit, Wong Chun Yong, and Ti Wei Ki. First of all, for introduction, this project mainly focuses on how to design a piping system layout. To design, we have to select a suitable pump specifications. For the objectives, we have to understand the principles of piping system and pump, and also we will perform theoretical calculations based on each formula, and also we will use a simulation called Pipe Flow Expert to simulate the whole thing. So as for the conditions, we must keep the fluid velocity below 3 meter per second. Then the capacity of water is 5 meter cube per second. As for the pressure drop in the condenser is 6 meter of water cage. The vertical distance between pump centerline and cooling tower top is 20 meter. Pump location is 5 meter below tower basin, and finally reduce condenser temperature from 30 degrees Celsius.
My name is Ti Wei Chi. Now, let me talk about the theory and concept of piping design and pump selection. First is the piping design. Designing an efficient and reliable piping system involving adhering to key principles to ensure optimal operation and longevity. These principles include maintaining appropriate flow rate and velocity, managing pressure drop, and addressing temperature change. The flow rate usually between 1 to 3 meters per second to avoid noise, vibration, and erosion. And the pipe diameter, we use the equation T equal to such 4Q over pi V. D is the pipe diameter, Q is the flow rate, and the V is the velocity of flow. And the second is the pressure drop management. The pressure drop we calculate by using the Darcy-Weisbach equation, where F is the Darcy friction factor, L is the pipe length, T is the pipe diameter, and the rho is the flow density, and V is the flow velocity. Managing pressure drop ensures the pump can provide sufficient pressure to overcome this loss. And the pump selection, first flow rate and total dynamic head. In selecting the appropriate pump involves ensuring it can handle the desired flow rate and total dynamic head. The total dynamic head comprises the elevation head, pressure head, and friction head. And the centrifugal pump. Centrifugal pumps are commonly chosen for their efficiency and suitability for consistent flow rate. It is crucial to select a pump whose performance curve match the system required flow rate and the total dynamic head. And the issue to take note, to avoid insolent section when using fixed control graph of other similar components, ensure every section has a pressure reference point, such as a tank of pressure boundary. Setting appropriate inflow and outflow demand and not help maintain continuity in the system. Now, let me talk about the methodology. The first defined requirement. The design approach for the piping system began with defining the requirement and constraints, including the desired flow rate, acceptable velocity limit, and the necessary pressure drop across the system. And the second, calculate pipe size. Calculations for the appropriate pipe size are conducted to ensure flow velocity remains within the range of 1 to 3 meters per second. And the third, determine total head required by pump. Key parameters such as flow rate, pressure drop, and total dynamic head are determined using fluid dynamic equation and industry standard. And the fourth, calculate pump power. We're using the hydraulic power equation for calculate the pump power. And the number 5, use pipe flow expert to simulate full flow. The software like Pipe Flow Expert may be explored to modern the system and verify the initial design calculation ensuring all components work within the defined parameter. Number 6. Create model and run scenario. Detailed model of the piping system are created, inputting the calculation parameter and running various scenarios to observe system behavior under different conditions. Number 7. Make comparison between the theory and the simulation. The simulation results are compared with theoretical calculation to ensure the accuracy and reliability. Adjustments are made based on the simulation outcome to fine-tune the design, ensuring optimum performance and efficiency of the piping system.
I will talk about the pump specification and the pipe size selection. So this is the theoretical calculation for this assignment. So the given capacity of the water cube equals to 5 millicube per minute. So we change to 5 millicube per second is 0.0833 meter cube per second. So chosen velocity will be 2.653 meter per second. So the given diameter formula is D equals to square root 4Q over pi V. So we will sub the value into the D to find the D. Square root 4 times 0.0833 over pi times 2.653. So we'll get the diameter of the pipe is 0.20 meter. So the viscosity of the water at 30 degrees Celsius will be 0.000792. So to find the Reynolds number, you use the formula of rho V D over viscosity. So the rho will be 1000, then multiply velocity 2.653 times the diameter 0.20 over the viscosity 0.000792. Then we'll get the Reynolds number of 665.58 kilo. So since the Reynolds number is bigger than 4000, then we can make a conclusion that the water flow in the pipe is turbulent. Next, we will go through the diagram given from the lecturer, that we can see that they are given 5 units of 90 degree elbow, 3 units of gate valve, 2 units of condenser exit, and 2 units of condenser entrance. So we will use the head loss calculation. H loss equals to K multiply V squared over 2G. So the loss coefficient we use at the 90 degree elbow will be 0.84. The loss coefficient at K at the gate valve will be 0.2. Loss coefficient at the condenser exit will be 1, and loss coefficient at the condenser entrance will be 0.5. So we sub all the value into the head loss calculation. B will be using 2.653, then G will be using 9.81. So we will get the head loss per unit will be at the 90 degree elbow will be 0.3013, gate valve will be 0.0717, and the condenser exit will be 0.357, and the condenser entrance will be 0.1793. So for the friction factor, the formula is F equals to 64 over Reynolds number. Then we will get the friction factor of 96.15 times 10 power of negative 6 Hz. Then we will find the major head loss. So the major head loss, the formula will be F multiply LV squared over 2DG. So substitute all the value inside, we will get the value of 3.622 multiply 10 power of negative 3. Then we will find the minor head loss. The minor head loss will be using the head loss of 90 degree elbow, head loss of gate valve, head loss of condenser exit, and head loss of condenser entrance. So add up all the value, we will get the 2.7959. Then the head loss will get 8.799 meter. Then the head pump will be 3.799 meter. Then we will have to calculate the pump power calculation. Hydraulic power equation will be P equals to rho G Q H per N. Then we sub all the value, we will get 24.207 kilowatt. So this is the design pumping system based on the question given. So we can see that the blue color one is the tank. This one is the pressure pump. This one is the pump. The red arrow is the pump. Then green color one is the pipe. This one is the valve. There are three valves. Okay. Then this one is the condenser exit, condenser entrance. So we will using the pipe flow expert to do this design piping system. Furthermore, this is the pipe data given from the simulation. So we will set the fluid zone. The water temperature is 30 degrees Celsius. The inner diameter calculation is all is 200 mm. Then is equal to 0.2 meter. So we are using different length of pipe. Then the mass flow kg per second will be the same for all pipe. Then the volume flow meter cube per second will be the same for all pipe. The velocity is the same for all pipe, 2.653. So this will be same as the calculation. And this is the pipe result get from the simulation. Then the pump result will also be given.
Okay, so now I'm going to go through the discussion. For the design process, we decided to use a pipe sizing of 200 mm diameter, which can help us to achieve velocity below 3 meter per second, which is 2.653 meter per second. For the flow calculations, continuity is achieved by using the formula A1V1 equals to A2V2, and then after calculation we get a Reynolds number of 665.58 K, which is more than 4000, which indicates that the water flow is turbulence. Then for pressure top and head loss, we use Darcy-Weisbach equation to solve. The total head loss we obtain is 8.799 meter, required pump head is 23.799 meter, and hydraulic power required is 24.2 kilowatt. Okay, now for the simulation results. We have, after going through the simulation, we have validated the theoretical calculations, which is quite similar. Okay, so first of all, pipe specifications, we decided to use steel pipe, which have a lot of advantage. First is corrosive resistance, and it has smooth surface, which can reduce the friction loss. Then the roughness is 0.046 mm, inner diameter is 200 mm, wall thickness 8.179 mm, outer diameter is 216 mm. So the velocity is just as the theoretical calculated, which is 2.653 meter per second. Okay, now head loss and pump head is 8.799 meter and 23.799 meter, which matches the calculation. And lastly, required power is 24.2 kilowatt, which is consistent with the calculated value. Okay, so now for conclusion, the design piping system is a success. The velocity we obtain is lesser than 3 meter per second, which suits the condition, and the pressure drops is managed effectively. After we go through the theoretical calculation and simulation value, the value we obtain is quite similar, and so the value is validated. Thus, a good and reliable piping system is successfully designed. Thank you.